This is SpaceTime, Series 20, Episode 12, for broadcast on the 15th of February, 2017. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe. You can download SpaceTime as a free twice-weekly podcast just about everywhere, including iTunes, Stitcher, Pocket Casts, Bytes.com, YouTube, SoundCloud, Audio Boom, and from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C. Coming up on SpaceTime, Pixies, Elves and Sprites seen from the International Space Station, new questions about Martian water, and how Earth's oxygen levels increased when the planet became a snowball. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Pixies, elves, red sprites and blue jets have all been seen by the crew aboard the International Space Station. And no, before you ask, it wasn't some alcohol-fueled orbital bender, but rather preparation for a new mission focusing on these mysterious, rarely seen phenomena associated with upper atmospheric electrical discharges. Apart from occasional reports of strange lights seen above thunderstorms by airline pilots, little was known about red sprites, blue jets, pixies and elves until a couple of decades ago, when scientists studying thunderstorms from mountaintops began picking them up in photographs. Then in 2015, European Space Agency astronaut Andreas Mogensen was asked to keep an eye out for these little understood lightning discharges during his stay aboard the International Space Station. Using a highly sensitive digital camera, Mogensen photographed and filmed numerous thunderstorms from his 400-kilometre high perch, capturing the rare red sprites, blue jets, pixie and elf light shows on several occasions. Denmark's National Space Institute has now published the results, confirming many kilometre-wide blue flashes around 18 kilometres in altitude, including one pulsating blue jet reaching some 40 kilometres into the sky. A video recorded by Mogensen as he flew over the Bay of Bengal at 28,800 kilometres per hour provided the clearest ever view of these rare electrical phenomena. Satellites had probed these events previously. The problem is their viewing angle wasn't ideal for gathering data on the scale of the blue jets and other similar discharges. Another attempt was made by the crew aboard the Space Shuttle Columbia. However, the destruction of the spacecraft and the loss of the crew during atmospheric re-entry also resulted in the loss of all that data. Now a new attempt by the crew of the orbiting outpost shows that they're in an ideal orbit to capture the sprites and jets. Mogensen aimed for cloud turrets, huge cloud pillars extending into the upper atmosphere. He shot a 160-second video showing some 245 blue flashes from the top of a turret drifting from the Bay of Bengal's thunderstorm. The blue discharges and jets are examples of a little understood part of Earth's atmosphere. Electrical storms reach into the stratosphere and have massive implications for how our atmosphere protects us from radiation. They also discharge minor gamma-ray bursts of their own. The images captured by Mogensen confirms that the space station is a suitable base for observing these phenomena. As a follow-up, the Atmosphere-Space Interactions Monitor is now being prepared for launch later this year. It'll be installed outside the European Space Agency's Columbus laboratory aboard the space station, from where it'll continuously monitor thunderstorms, gathering information about these transient luminous events. Mogensen says it's not every day you get to capture a new weather phenomenon on film.
I had a chance to work on a Danish experiment called Thor, which is actually a precursor to a larger experiment called ASIM, which will be launched into space in the next couple of years. The purpose of ASIM is to photograph and study some of these lightning phenomena that we call blue jets and red sprites. And these are lightning that shoots up into space or up towards the outer edges of our atmosphere rather than down to the ground. We don't know very much about it. We don't know how often these lightning phenomena occur or under what conditions or what effect they have on our atmosphere. But the purpose of Thor during my mission was simply to try to take some pictures or video of some of these lightning phenomena. One evening I was sitting in Cupola and we were flying over India when I saw this gigantic thunderstorm begin. So here you can see a gigantic thundercloud that's lit up by what we would call traditional lightning. These red sprites, so this is red lightning that's shooting upwards out towards space at the same time that there's traditional white lightning that we know. And as I looked further, I also saw this blue jets, so blue lightning again shooting up into space. And I actually managed to capture that on film. According to the researchers, this is the first time they've ever seen this blue lightning shoot up like that. So they are very, very excited about it and have already started to analyze the data to try to get a better understanding. It bodes very well for the future when ASTM will be up there in the next couple of years. And hopefully ASTM will help us to understand this much, much better. Because as I said, it's something that we know very, very little about at the moment.
European Space Agency astronaut Andreas Morgensen during a recent press conference. Red sprites are transient vertical column-like plasma structures. They're often seen in reddish flashing clusters at altitudes of 50 to 90 kilometres. Red sprites are thought to be large-scale electrical discharges triggered by positive lightning. Positive lightning is a rare type of lightning. It originates in the anvil head of a thundercloud where positive charges tend to accumulate. Positive lightning is about 5 times as powerful and hot as normal lightning seen from the ground, which is known as negative lightning. Unlike negative lightning, which occurs either inside a cloud or from the base of a cloud to the ground, positive lightning travels outside the cloud, striking the ground directly. The lightning bolts also last about 10 times longer, allowing it to strike many kilometres away from the storm, and that's led to the famous expression, like a bolt of lightning out of the blue. Sprites are also sometimes associated with reddish halo emissions, lighting for up to a millisecond before the sprite and around 70 kilometres above the initiating lightning strike. Sprite halos often look like 50 kilometre wide flat discs. They're believed to be produced by a weaker version of the same ionisation process that generates sprites. On the other hand, blue jets, which are related to sprites, are very bright narrow cones of plasma seen above thunderstorms at altitudes of 40 to 50 kilometres. It's thought they may be triggered by strong hail activity during thunderstorms. Their blue and near-ultraviolet colour emissions are thought to be caused by neutral and ionised molecular nitrogen. More powerful versions known as gigantic jets can be up to 70 kilometres long, while shorter, brighter versions of blue jets, known as blue starters or gnomes, are often seen at altitudes of up to 20 kilometres. Pixies are pinpoints of light, lasting less than 16 milliseconds on the surface of convective domes that produce gnomes. Another related phenomena are called trolls. Trolls look like blue jets but are red in colour and seem to occur after tendrils of vigorous sprites extend downwards towards the cloud tops. Elves are flattened, expanding reddish glows of plasma up to 400 kilometres wide but lasting for just a millisecond. They've been seen at altitudes of 100 kilometres above thunderstorms and are thought to be caused by the excitation of nitrogen molecules due to collisions between electrons, energised by lightning from the underlying thunderstorm. You're listening to SpaceTime. I'm Stuart Gary. New evidence about carbon dioxide levels on ancient Mars have raised fresh questions about how liquid water could have existed on the red planet's surface billions of years ago. A report in the Proceedings of the National Academy of Sciences claims an analysis of samples taken by NASA's Curiosity rover indicates Mars simply didn't contain enough CO2 in the atmosphere for liquid water to have existed in Gale Crater, despite clear geological evidence that it was there and present for long periods of time. Curiosity found that the level of CO2 in the atmosphere at the time the Gale Crater sediments were deposited were between 10 and 100 times less than the minimum required for the surface temperature to be above the freezing point of liquid water. The area Curiosity has been analysing since 2012 is located close to the Martian equator. It's composed primarily of sedimentary sequences deposited at the bottom of a lake 3.5 billion years ago. These sediments contain various secondary minerals such as clays or sulfates, which indicate the past presence of liquid water. One of the study's authors, Alberto Ferrin from the Centre for Astrobiology near Madrid, says the existence of liquid water requires a warm surface temperature brought about by a minimum content of CO2 in the atmosphere. However, he says this is simply not the case with Mars in its beginnings. The findings mean that either scientists don't fully understand the climatic and environmental conditions on early Mars, or Gale Crater sedimentary sequences somehow formed in a very cold climate despite its location near the Martian equator. Curiosity's failure to detect carbonate supports similar findings by other probes, which also concluded that Martian atmospheric CO2 levels must have been very low. On Earth, carbonate deposits form on lake and seabeds when CO2 in the atmosphere interacts with liquid water. Of course, carbon dioxide is a gas capable of generating a powerful greenhouse effect and therefore heating the planet. According to Ferran, an image which may well describe Gale Crater in the early days of Mars would be one that includes a glacial lake surrounded by huge masses of ice which would be partially or seasonally frozen. He speculates the environment would be similar to the Canadian Arctic or Greenland today. In addition, although ice would have dominated, Ferran thinks it would also have been common to find liquid water present in abundance. The formation of clays and sulfates would have occurred at specific places and times, seasonally or under an ice cap in liquid water lakes. You're listening to SpaceTime. I'm Stuart Gary. Okay, let's take a break from the show and talk about one of our sponsors. Audible's offering a free audiobook download with a 30-day trial to give you an opportunity to check out their service. Audible have over 180,000 different titles to choose from, such as Contact by Carl Sagan or A Brief History in Time by Stephen Hawking. Others include the unabridged version of The Hobbit by R.R. Tolkien, Divergent by Veronica Roth, and Born to Run by Bruce Springsteen. So many great books no matter what your taste, over 180,000 titles to choose from. To download your free audiobook today, go to audibletrial.com/spacetime. That's audibletrial.com/spacetime for your free audiobook. Or you can click on the link at spacetimewithstuartgary.com. And now, back to our show. A new study has found that oxygen levels on Earth increased after the entire planet was covered in massive ice sheets, forming a Snowball Earth hundreds of millions of years ago. That increase in atmospheric oxygen levels allowed for the development of more complex life forms, eventually leading to humans. A report in the Journal of the Proceedings of the National Academy of Sciences claims planet Earth's atmospheric oxygen content began to increase about 2.4 billion years ago, at the same time as a Snowball Earth global glaciation. The Snowball Earth event occurred at a time when all the continents were gathered into a single huge landmass or supercontinent. How to explain the exact connection between these events, however, has been a question which has baffled scientists for years. One of this study's authors, Professor Olof Sunderland from Sweden's Lund University, says the results show that oxidation coincides in time with an event of global glaciation of the Earth and extensive volcanism. The authors pinpointed the timing of the so-called Great Oxidation event from volcanic rocks in South Africa. They linked it to a global glaciation or Snowball Earth event which occurred some 200 million years earlier than previously thought. The global glaciation meant that most of the planet was covered in ice. Snowball Earth events are believed to have occurred several times during the planet's history, the last approximately 600 million years ago, and that was also followed by a significant increase in Earth's oxygen content. The new study shows the emergence of oxygen took place at a time when most of Earth's land masses were gathered into a single supercontinent called Kenneland. Paleomagnetic studies show this continent existed around the equator and was largely covered by volcanic lava. Initially, the increase in oxygen in the atmosphere was not a steady process, but characterized by substantial fluctuations. The authors were able to link the oxygen fluctuations to a very unstable climate which may have arisen due to volcanic activity on the supercontinent. Sunderland says although the exact relationship between the oxygen rise, volcanism and global glaciation remains uncertain, the new findings finally provide consensus about the time these events affected the Earth. Meanwhile, previous studies have concluded that extensive underwater volcanism caused by the breakup of an ancient supercontinent may well have pushed the Earth into a period of extreme freezing 750 million years ago from which the planet almost didn't recover from. That hypothesis by Professor Elko Rowling from the Australian National University provides a single mechanism to explain different aspects of the Snowball Earth event. It was thought that runoff from rivers into the oceans, caused by the breakup of the Rodinia supercontinent, caused changes in ocean chemistry, which reduced atmospheric carbon dioxide levels, resulting in increased global ice coverage. These vast continental ice sheets reflected sunlight away from the Earth, further cooling the planet and pushing it past the tipping point into a snowball state, where the ocean started freezing over as well. The planet remained locked in Snowball Earth for millions of years. However, eventually, volcanism pumped enough CO2 back into the atmosphere to warm things up again. Thick deposits of carbonate rocks such as limestone, known as cap carbonates, were deposited as the Earth warmed. The computer models developed by Rowling and colleagues showed how the breakup of Rodinia generated extensive shallow marine volcanic activity, producing large amounts of glassy volcanic rock called hyaloclast. These readily break down, releasing large amounts of chemicals which saturated the oceans, turning them rich in calcium, magnesium, silicon and phosphorus. This in turn drew carbon dioxide out of the atmosphere and cooled the planet. Eventually, as the Earth warmed up again and the ice sheets broke apart, light penetrated the oceans, allowing algal life to pick up again and undertake photosynthesis. Phosphorus, leached from the hyaloclast minerals, provided enough nutrient to allow huge algal blooms to form, fixing carbon and releasing oxygen, which then allowed other more advanced life to develop and eventually take hold. I'm Stuart Gary. This is SpaceTime. You may recall a couple of weeks ago we reported how astronomers have found a missing link between neutron star pulsars and highly magnetic neutron stars known as magnetars. That study, published in the astrophysical journal Letters, suggested a mysterious object called pulsar-J1119-6127 could be in the never-before-seen transition state between a pulsar and a magnetar. Since the 1970s, scientists have been treating pulsars and magnetars as two very distinct populations of neutron stars. A pulsar is a rapidly rotating neutron star, the extremely dense stellar corpse of a massive star which exploded at the end of its life in a core collapse or Type II supernova. Pulsars emit radio waves in predictable pulses due to their fast spin, which causes them to shine like rotating lighthouse beams visible across vast areas of the local universe. By contrast, magnetars have violent high-energy outbursts of X-rays and gamma-ray radiation, and they generate the strongest known magnetic fields in the universe. The detection of PSR J1119-6127, acting as both a pulsar and a magnetar, supports a growing body of evidence over the past decade that these objects could be different stages in the evolution of the same thing. If that's the case, this discovery represents the final missing link in the chain that connects pulsars and magnetars. It appears to provide a smooth transition between these two kinds of neutron star behaviours. Sometimes it's a pulsar, other times it's a magnetar. As a result, this object may also tell astronomers something new about the underlying mechanisms of pulsars in general. When this mysterious object was discovered in the year 2000, it appeared to be a radio pulsar. It was mostly quiet and predictable. That was at least until July 2016, when NASA's Fermi and Swift space telescopes both observed 2 X-ray bursts and 10 additional bursts of light at lower energies coming from the object. An additional 2016 study also looked at the 2 X-ray bursts, incorporating observations from NASA's New Star Space Telescope, the Nuclear Spectroscopic Telescope Array, which suggested that the pulsar was behaving rebelliously like a magnetar. Astronomers quickly turned NASA's Deep Space Communications Network 70-metre dish in Canberra, the largest radio dish in the Southern Hemisphere, to see what was going on. They concluded that these X-ray bursts were happening because the pulsar's enormous magnetic field got twisted as the object was spinning. The stress of the twisting magnetic field was so great it caused the outer crust of the neutron star to break, analogous to tectonic plates on Earth causing earthquakes. These stellar quakes on the neutron star caused an abrupt change in rotation called a glitch, which was detected by a new star. With the exception of black holes, neutron stars are the densest known objects in the universe. In fact, 1 teaspoon would weigh as much as a mountain. The crust of a neutron star is thought to be about 1 kilometre thick, with higher pressure and density at greater depth in a neutron-rich lattice. And this particular neutron star is thought to have one of the strongest magnetic fields among the population of known pulsars, trillions of times stronger than the magnetic field of our Sun. 2 weeks after the X-ray outburst, astronomers tracked the object's emissions at radio frequencies which are much lower in energy than X-rays. The radio emissions had sharp increases and decreases in intensity, allowing scientists to quantify how the emissions evolved. researchers were able to use an instrument informally known as the pulsar machine, which was recently installed on the 70-metre Canberra deep space dish. Within 10 days, something completely changed in the pulsar, and it began acting more like a normal radio pulsar again. Astronomers, including the CSIRO's Shinji Hiroshi, continued to monitor J1119, observing a marked brightening of emissions at radio wavelengths in a pattern consistent with other magnetars. But the question remains, which came first, the pulsar or the magnetar? Some scientists argue that objects like J1119 probably begin as magnetars and gradually stop outbursting X-rays and gamma rays over time. However, others propose the opposite theory, that the radio pulsar comes first, and then over time its magnetic field emerges from the supernova's rubble, and then the magnetar-like outbursts begin. To help solve this mystery, astronomers want to find more missing link objects like J1119. This particular object likely formed following a supernova 1600 years ago. Shinji Hiroshi says monitoring similar objects may shed fresh light on whether this phenomenon is specific to J1119 or whether this behavior is common in this class of objects.
Because we are using excellent radio telescopes, especially 7-meter dish is the largest in Southern Hemisphere, NASA allows Australian community to use as a radio telescope, not just for tracking spacecraft. They want sometime to use the dish as a radio telescope to observe directly stars and galaxies. And we're typically using the gap between spacecraft trackings. So that for that time, we use this to observe like pulsars or active galactic nuclei and that kind of stuff.
And that's where this research came in with this neutron star, which sometimes acts like a radio pulsar, but other times acts like it could be a magnetar.
That's right, yeah. So, just by coincidence, JPL set up project to observe pulsars. Original purpose was to search for pulsar near our galactic center. Then this pulsar J1119 minus 6127, this became bursting, and it behaved as a burster, magnetar. It was originally like normal pulsar, and following this news coming among astronomy communities, we started observing this pulsar.
To do this, you used a new piece of equipment that was added to the telescope, informally referred to as the pulsar machine.
That's right, yeah. Just simple naming, but So this machine is taking entire band we can observe with the telescope, and which is so capable for this kind of project. Yeah. Normally for spacecraft, we are only dealing with very narrow chunk of the band because spacecraft carrier is very narrow. But for pulsar, they emit what we call continuum emissions, which is very broad. So we want to record as much as possible to gain the sensitivity. And also, pulsar behaves slightly differently depending on the frequency of observed. So we want, of course, as much information as possible, which is very suitable for pulsar research.
Is there a great deal of difference between a radio telescope and a communications dish?
The only difference is what kind of a frequency and what bandwidth you want to observe.
So it just depends what you want to listen to.
That's right, yeah. Correct.
We've seen radio dishes like Arecibo used to actually take radio images of asteroids and things like that. And is that something that the Deep Space Network's Canberra dish can do as well?
Correct, yeah. So radar projects, so NASA has been doing radar projects using this space network facilities and also big dish like Arecibo or Greenbank radio telescope. And we also started, so that has been mainly in Northern Hemisphere, but also from Southern Hemisphere. We tested radar experiment last year. Yeah, so it's been progressing well, yeah.
Yeah, I know that NASA have been doing some work looking at Bernoullian radio frequencies. This is the asteroid which will form part of the OSIRIS-REx mission, the first mission by NASA to do a sample return to an asteroid.
Yeah, that's correct, yeah.
That's Shinji Hiroshi from the CSIRO, who's based at NASA's Deep Space Communications Network in Canberra. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, and from SpaceTimeWithStuartGary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C.
This is SpaceTime with Stuart Gary. For more, you can follow us on Facebook, Twitter, and Tumblr. Just search for SpaceTime with Stuart Gary.
SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.